Tēnā koutou, tēnā koutou, tēnā koutou katoa, and welcome, distinguished guests, colleagues, ladies and gentlemen. This is 19th annual ST lecture in Antarctic Studies. My name is Ehsan Mesbahi. I'm the Pro-Vice Chancellor for the Faculties of Science, Health, Engineering, Architecture and Design Innovation. And it's my pleasure to be your host tonight. I would like to extend a particularly warm welcome to Professor Robin Bell and Carl, her husband, our guest speaker for this evening. Just had a conversation with Robin and going off the notes at the moment. I think I'm going to get in trouble later. I've just had a conversation and I was given a challenge of to guess how Robin and her husband got here. And I couldn't guess. I think I used to sail on ships, and I never thought that Robin and her husband got here on a boat all the way crossing the Pacific Ocean. I mean, seagoing engineers really don't like to go through Pacific Ocean because any danger you get at the middle of that is going to be very difficult to get help. And I really admire your courage to get on your boat, sailing boat, with just a very little engine to get all over to New Zealand. Well done. This is amazing. And I'm sure it was very environmentally friendly as well. Your carbon footprint was almost zero. Well done. Professor Bell is here tonight because of the generosity of the Lee Foundation on behalf of Dr. Lee Sung Tee, for whom this annual lecture is named. I would like to acknowledge the passing of Dr. Lee in July this year and note that tonight's lecture is a tribute to his extraordinary record of philanthropy and support of education and learning, which spanned several decades. The university is grateful for the continued support of the Lee Foundation in their efforts to foster excellence in education and research. We are privileged to be one of the universities bestowed with Dr. Lee's generosity and honored to be included alongside prestigious universities like Oxford, Cambridge, and Harvard, which have all been benefited from the Foundation's support with building libraries, offering fellowships, and hosting annual lectures. Events such as this lecture contribute to the world-leading scholarship undertaken by the university's Antarctic Research Center in their goal to better understand Antarctic processes and their influence on the global climate system. Our university's involvement in Antarctic research goes back over 60 years. The Antarctic Research Center was formally established in 1972, and our university has this year celebrated 50 years of providing a platform for our scientists to lead the way in developing drilling systems to extract geological samples and better investigate ancient climate changes on the Antarctic continent. The center also offers teaching and government advisory services with several staff involved in prominent international efforts such as Intergovernmental Panel on Climate Change. More recently, by working closely with our partners such as GNS and NIWA, our Crown Research Institutes, the center has become a global leader in the computational modeling of glaciers and ice sheets in response to climate change. It has grown to be recognized as a world leader in Antarctic science and a key player in major research operations, attracting significant government investment and interest. The Antarctic Research Center's work contributes significantly to our university's effort to enhance resilience and sustainability, maintain research partnerships with local and global organizations, and contribute to the resolution of some of the most pressing challenges facing our Earth. The annual ST Lecture is an important event in the Centre's calendar. It provides a valuable opportunity to hear from an internationally renowned guest speaker and to celebrate the successful research and collaboration programs being undertaken by our scientists. Our speaker tonight, Professor Bell, specializes in geophysics, particularly in relation to ice sheets, with her research focusing on understanding how they work and will change in the future. Professor Bell directs research programs in both Antarctica and Greenland and has developed technology to gain new insights into our changing planet. Her research has led to a number of important scientific discoveries, including the detection of volcanoes beneath the West Antarctic ice and several large lakes sealed deep beneath the ice. In fact, her work has been so impactful that she has an Antarctic mountain named after her. So this is the time all of you get more jealous. During her career, Professor Bell has contributed to over 100 peer-reviewed publications, as well as a US Senate testimonies, National Academy reports, and popular media publications. She has held several high-profile leadership positions in polar science, such as a Fellow of the American Geophysical Union, of which she was president between 2019 and 2020. Professor Bell is currently a research professor at the Lamont Doherty Earth Observatory at Columbia University. So without further ado, please join me in welcoming Professor Robin Bell to the podium.
Thank you very much, Dean. Tina koto ka toto. Ko Robin Bell tuku nago. Ko Adirondacks te Munga. Ko Hudson te Awa. Ko Columbia University te Iwi. Ko Maple Rose te Waka. Na mihi nui ki a kawa. Thank you very much for having me. I'm very honored. My name is Robin Bell. The Adirondacks, where we went during the pandemic and where my family celebrates things large and small, is my mountain. The Hudson River, where we sailed out of to come here, is my river. It's a river where I've seen tremendous change. When Carl and I first went down the river, when we were just out of college in a small wooden boat without an engine, even worse. We had to row. The river was very dirty, and one couldn't imagine wanting to touch it. The river now is clean enough that our children swam in it when they grew up, and it's a river that gives me hope as we look at our planet today. Columbia University has been my home for decades. I've been very honored to work at Lamont Doherty, and the Maple Rose is the name of our boat on which we got here. So thank you very much. I'm very honored to be here today. But I am really simply the storyteller. Science is a total team sport. We are working together to build this body of knowledge, to push it, to find out where we disagree, where the bumps are, where things aren't quite right. And it takes many people. It takes pilots. It takes people who do logistics. It takes engineers and scientists. And so I am really just here today as the spokesperson for all these people who have helped me over the years and helped basically us as a species, because we are in a unique position as a species that we can see how our planet works, and even more importantly, actually understand how our planet is changing and what we spent a lot of this afternoon discussing can we make robust models to predict the future of our planet? So it really is, I am just the storyteller of Antarctic ice today, and I hope by the time we're done, you will have some of my wonderment about how old it is, how beautiful it is, and understand why it is unforgiving too. So that's the journey I hope we're going to take today. When you think of Antarctica, depends on where you're from, what you think about. You might think of a map like this, kind of like an elephant's head maybe. Or maybe you think of something like penguins running all over the place, beautiful penguins jumping in. But everybody has a different picture of Antarctica. But when I close my eyes and think of Antarctica, this is what I see. This is a picture from the top of the ice sheet, very close to Dome. I think of this landscape. It's kind of like being in the ocean, in that the horizon is tremendous. Maybe the desert's the same way, where the sky goes on forever. But here, the sky is an intense blue. It's blue because the atmosphere is so thin. There's actually less clouds, there's less moisture, so the sky is this intense blue. And then when you lie down on the ice sheet and close your eyes, all you can hear is the tinkle of the snow crystals bouncing across the snow surface. Antarctica is a very special place, and my job has been to see if I can look through that ice. Right here, the ice is between 3 and 4 kilometers, and I can't hear much putting my ear down except for those crystals bouncing across the surface. So I hope that you'll both walk away with a sense of wonder and beauty, but also of the mysterious things beneath the ice sheet. There are 2 ice sheets, it turns out, in Antarctica. We kind of think of it as one big lump of ice, but in fact there are 2. It's controlled by the geology, and very cleverly there's east, which is what if we went straight south, I'm a little turned around. If we went straight south from here, we would hit East Antarctica. It's a big piece of ice, and we'll come back, and by the time you walk away, you'll understand it. It's the old piece of ice. It's thick, it's old, it's sitting up high. And then the one that you might have heard people worry about a little bit more is called West Antarctica. It's cleverly in the Western Hemisphere mostly. That's where it gets its clever name. And it's younger. It's more sensitive to climate change. And it's a little bit more dynamic, as we'll see. So that's sort of your introduction to, we're going to come back to this a couple times, to the 2 parts of Antarctica and the 2 ice sheets that it holds. But I thought we'd just start with how old is Antarctica and when did it get covered in ice? First, let's just look at those little bouncing balls at the top. And if you start on the side closest to me, so on your left side, if you're good at left and right, you can see what Antarctica looked like, 45 million years ago, which is geologists not really that long ago. You can see there was no ice in Antarctica. It was exposed. There might have been some ice in the mountains. The interesting thing was CO2 in the world was higher and temperature was higher. So there once was a unglaciated Antarctica, which had, trees that might not have been that different than some of the trees here in New Zealand. You might have recognized it if you were time traveled back. And then if we travel through time, going away from me towards the other side of the room, you can see that over time CO2 starts to drop. And global temperature, that's the bottom plot, you can see global temperature rolls off. The world was much warmer. It was when Antarctica had no ice, it was on the average of 25 degrees C. It was a normal temperature. And as the temperature of the planet got colder and colder, it eventually hit a moment about around 34 million years ago where Antarctica became glaciated. East Antarctica became glaciated first because, as we'll see, it sits up higher. It's easiest to grow glaciers on high mountains. And then the world got colder, and eventually it's really hard to grow an ice sheet in West Antarctica because, as we'll see, it's a shallow ocean, and it's really hard to cover a shallow ocean in ice. But you can see eventually in that middle ball, eventually over on the left, you'll see that West Antarctica got covered. And then in the last period of the planet, we had this oscillation between when the ice sheets grew and the ice sheets shrunk. And that's the top. You can see the top right is a sort of a basketball picture of what it looked like when the ice sheet shrunk, during an ice sheet collapse. And then on the bottom one, you see what it looked like probably during the last glacial maximum, about 25,000 years ago. And and how do we know that? We know that from the climate records in the sediments, in the ice cores, and that bottom condition where you see Antarctica looks much whiter, that's when North America also was covered with ice, when New York City was covered with ice. And essentially the bridge, if you've ever seen the start of the New York City Marathon, is across a bridge called the Verrazano Narrows. That, in essence, marks the southern extent of a Laurentide ice sheet. That actually bridge goes across the terminal moraine of a Laurentide ice sheet. So if you think of how far south did the ice sheet go, think of the start of the New York Marathon in North America. So there was a lot more ice, and it's come and gone on about 100,000 year cycle. So we're currently in between those two, obviously, between the glacial maximum and the marine ice sheet collapse. And just as an aside, when I started graduate school, there was still a discussion were we about to go into another ice age? That was the conversation in the halls from a number of very prominent scientists who now, and then I remember as a graduate student hearing the conversation shift to, no, the climate is warming, and that's the consensus that's certainly built over time. So what does Antarctica look like? These are some of my favorite pictures. The one on the left sort of shows you how the ice sheet flows. In the middle, it's pretty stable. It moves, maybe across the podium in a year, really slow. But on the edges, you can see little hints of rivers. Those rivers are going kilometers a year. Those are the engines in Antarctica that pull the ice from the interior and deposit it in the ocean. Those are the mechanisms that in the future will move ice into the global oceans and cause sea level. But what does it look like underneath? I've kind of been alluding to the two ice sheets being very different. And so on the right, you can see what the topography looks like underneath the ice sheet. Anywhere that's blue is below sea level, and anywhere that's green or brown is above sea level. So you can see how different the two halves of Antarctica are, that one is really a shallow sea, and the other is a continental plateau, something like, say, Africa or Australia, or maybe even India, given that geologically that's where its siblings are, shall we say. That's what sat next to Antarctica before Gondwana broke up. So let's step through and look. So this is if we look at those cross sections. If you like to look at cross sections, I do. The top one is across East Antarctica, and what you can see is that East Antarctica is pretty much above sea level. There's a lot underneath, and we'll take a tour of East Antarctica, and then you can see West Antarctica is mostly below sea level. That the ocean is on the right, and it's very clear that, as I like to say, West Antarctica has her toes in the water, and that connection to the ocean means that in the future, not only as the climate warms, it is that the ocean being able to reach the base of the ice sheet, which makes the ice sheet inherently unstable. And we will warm both the atmosphere and the ocean, but that ability of the ocean to sneak in and reach the ice sheet where it's under water already is inherently an unstable position. So let's take a tour through how we built those cross sections. So over time, we've developed a couple of different techniques to measure how thick the ice is. In the 1950s, during the International Geophysical Year, dynamite and explosives were the preferred way of measuring, plus gravity, my favorite potential field, were the way to measure ice thickness. You can see on the left, you can see a tractor vehicle, kind of like the one Hillary drove across Antarctica. But you can also see this giant fountain of snow. That's not a volcano, that's actually an explosion. It means actually they didn't put it down deep enough because you'd hope the energy went into the ice instead of the air. But it's a dramatic picture and it gets you to understand that this is how we originally measured the ice thickness. Over time, we figured out that we could do it with radar, that was less energy intense, and that we could do it first by dragging a radar in a little wooden hut on skis behind a tractor, and then eventually putting it on airplanes. And that meant that you could look at a much bigger region of Antarctica. And it was the same idea on the right. You can see a ping going out from the airplane through the ice sheet and bouncing back. It's, just the same as figuring out how far away an echo is from a snap of lightning and listening to the thunder. And that allows you to time how far away the lightning is. We basically measure the time to the response of the radar to bounce off both the surface, all the layers in the ice, and the rock underneath. The middle is a picture of what a modern radar system, and this was from a project that I was part of that was joint with New Zealand and the US, where it's called the Rosetta, and we use this instrument called the IcePod, where this instrument that everybody's lying on, it snapped onto NEC-130 and allowed you to turn NEC-130 into an imaging machine. And it allowed us to look at what the water depths and the shape of the cavity are underneath the Ross ice shelf. So those are the ways you can either use explosions or radar to get a sense of what's underneath the ice sheets. So what does a radar image look like? I love radar. If I'd remembered, I would have brought my radar dress. I actually have an image of, I've made a dress that has radar on it just because what a beautiful way to look at our planet. But not having that, I'm going to have to show you it on the screen. And these are the layers. Each one of these is an isochron, or basically a year in time. It means some point in time where the electrical conductivity of the ice change. Could be a volcanic eruption, could be something that made the conductivity of the ice change, and so energy bounced off of that. So that's what those layers are. On the bottom, this zigzag, that's actually mountains underneath the ice sheet. And then in this valley, the very bright reflector is energy coming off of water. Water is a much better reflector than rock, so you get a stronger reflection back whenever you fly over water with a radar system. So this is what it looks like. This is an example of what the equipment we use in the interior, a Twin Otter with radar systems. And then because it's such an honor to be in Antarctica and you want to basically make sure you look at everything at once, we also put a laser system to match the ice surface, a gravity meter to measure basically the iron content of the geology of the topography underneath, and a gravity meter to get a sense of what the density of the rocks are. So doing everything we can when we're there. So this is, again, going back to East Antarctica. We're going to take a quick tour of both Lake Vostok here and the Gimbertsev Mountains. What you can see is this is the ice sheet over the top, where you go from the white to the light blue, and the dome is the very top of the ice sheet, Dome A. Currently the Chinese have a base here. Dome Fuji is where there's an ice core that the Japanese led drilling. Dome C is where the European consortium drilled an ice core, and Vostok is where there's during the International Geophysical Year, the Russians opened a base there because at that point it was close to the magnetic South Pole, and there's also an ice core there. But let's look at what it looks like. So if we look at a radar image, we can see that the ice over Lake Vostok, through a core, we know that the ice at the bottom is about 420,000 years old. So just, put that in perspective. Humans, Homo sapiens evolved about 300,000 years ago. So this ice is pretty much older than Homo sapiens, and this really isn't even the oldest ice in East Antarctica. It just was the first very, very deep ice core. One of the wonderful surprises of the Vostok ice core was when they got to the bottom and they found that they lost the climate record, and suddenly there wasn't the regular ability to look at how the isotopes were changing. The crystal sizes changed, and the electrical conductivity of the ice completely changed. At about the same time, we got the first image of the ice surface. So on the right-hand side, you can see it was on the cover of Nature because it was so groundbreaking then. It was the first time we were able to look at the ice surface, and you can see domes, right? You can see the divides, just like if you were to go hiking and you get to the top of a ridge, you can go down the other side. So we saw before Dome Fuji. This is where Vostok is, Dome Concordia. So when this came out, this is a wonderful example of international collaboration. What became very clear was there was this incredibly flat spot in the middle of the ice sheet. See how it kind of looks like a lima bean to me? How big is it? If one end of it was here, the other end would be at Christchurch. So it's a pretty big piece of flat ice. So the European scientists who saw this contacted the scientist who, as a young student, had done the seismic work during the International Geophysical Year. He was a very prominent Russian scientist, but was a little bit too Anglo. And he had misinterpreted it turns out he had shot off seismics, and he had concluded there was mud underneath the station. His parents had spent a lot of time in Cambridge, and that meant that he got exiled as a young scientist to Kamchatka. He left his records in the garden shed in Moscow. Many decades passed. This image came out. He had returned to Moscow, and these European scientists called up and said, "Do you have that data?" And he goes, "Let me go check." Well, the garden shed had burned down, but it turns out that in the wreckage of where the garden shed used to be, this is why you should save your data. This is really a data archive story. Your thesis might matter someday, just because you think it doesn't. You never know. So he went out to the garden shed. He found the records, and he found that he'd made a mistake in interpreting it. It actually wasn't mud. It was actually hundreds of meters of water underneath that very flat spot. So suddenly they were able to, this man who'd been exiled to Kamchatka for decades, was able to get a publication from his thesis on the cover of Nature demonstrating that there was a lake that over 250 kilometers long beneath the Russian station. Just so you know, you could identify a lake. This is what the surface imagery looks like. And if you've ever been up on a glacier, you know that a glacier is rough, right? See how rough the surface is here? That's because that ice is rolling over topography. It's reflecting the topography underneath. And if you've ever been ice skating, you know, or skiing over a lake, you know it's flat. That ice is floating. And that's what you're seeing here. You're seeing that the surface of Lake Vostok is dead flat. That's because there's water under there. And then, in case you think you can't make discoveries at an international meeting, I was looking at this image up on somebody's AGU poster, and they were showing Lake Vostok and all the wonderful images. And I kept on saying, but aren't these lakes over here on the right? If Lake Vostok's a lake, isn't that flat area on the right a lake? Anyway, 2 months, it was like one of those wonderful moments where 2 months later, the people at the poster session and I had written a paper and discovering these additional deep lakes. And they were actually the lakes that made me worry less about the Russian. There was no way the Russians weren't going to drill into Lake Vostok. It was their lake. And to me, my only comfort was knowing that there were these other big, deep old lakes that would be preserved, regardless of what the Russians did drilling into Lake Vostok. So it was my comfort when it became very clear that the Russians were going to drill into Lake Vostok regardless of what anybody else said. So that's the story of Lake Vostok and how it's both been, it was pretty much the first ice core record. And the reason ice core records are important is that they are the way we can actually capture old CO2. Right? We can't get that anyway except for the bubbles we can't get it really well at a high resolution anyway except out of ice cores. So it's a beautiful record of what our atmospheres used to look like back for 400,000 years. Dome Sea, the ice goes back 800,000 years. And groups are looking for ice that's more than 1 million. That is the goal. So let's take a look at this region, the Gimbertsev Mountains, because I do want you to walk away thinking, wow, the ice, Antarctica is a glorious place. It's hard to get to the central part of Antarctica. It's high, it's cold, it's very far from any logistics base. Here's South Pole, here's the Australian station, here's the Chinese station. You can see this is 5 degrees of latitude, so 500 kilometers. This is a long way, and it's a long logistics chain for anyone to work. So in essence, nobody had really systematically been back to this region since the Gimbertsev Mountains were discovered in 1958. They were discovered when one of those traverses drove across the ice sheet. And as they were going, they did gravity in between the explosions, and they kept on seeing the gravity was getting stronger and stronger, and every time they did the explosion, the ice was thinner. And they realized they'd discovered a mountain range, completely covered underneath the ice sheet by the ice. They named it after Gimbertsev, a famous Russian geophysicist. And even as a student, I used to hear rumors that there were outcrops, that there were some satellite images that showed the rocks of the Gimbertsev Mountain, but nobody had been back there since 1958. And it really took the framing of the International Polar Year in 2007, 2008 to get this is why I'm such a strong believer in international science, because when you can get multiple nations working together, you can do things that no single scientist, no single nation can do together. You can do things that are pretty much impossible. This is a region where there's about a month where the temperatures are above -50, which is about where the seals on the aircraft start working reliably. So you have a very narrow window where you can actually operate. So we did manage to get 7 nations together. The Australians built a camp in the north, the Americans built a camp in the south, the Chinese delivered fuel, the Americans airdropped fuel on this side and then delivered fuel to the south, and the British and the Americans each brought up airplane. And so in that narrow window, we were able to keep the plane in the air almost about 20 hours a day. We would land, refuel, pull the discs out. And what we went from was from this fuzzy, unknown topography to what you see on your lower right is actually the beautiful dendritic pattern of the mountains in in the Gamburtsev Mountains. Something that people were totally surprised about, that you would have that kind of structure underneath the ice sheet. As scientists, we'd of course had written a proposal that said we're going to look at lakes. And we didn't actually really think we were going to find lakes. It's like, yeah, we'll say we'll find lakes, but who's ever heard of finding lakes in a mountain range? Well, it turns out every single time we crossed one of these valleys, and I'll show you in a minute, we saw one of these bright echoes. There was water in all of those valleys. So this is really what it ended up looking like. Turns out that the upper layer is an indication of the dome of the ice sheet, Dome A, draped over the Gamburtsev Mountains, and in the valleys are water. Every single valley had water. Pretty cool. Then we began to think about how that water is flowing, right? Isn't that the next question? Where does the water flow? And we're so used to thinking water flows downhill. Right? That's kind of, we'll walk outside and look at the hill here and the water will flow downhill. Well, there's an ice sheet sitting on top of on all of those water systems. And the more we thought about it, the more we realized that a number of those systems, the water was being driven uphill. That these were actually a place in the world where we had backwards flowing rivers. And not fast. I mean, rivers is probably an exaggeration. How about a little bit of water flow seeping along the bottom of the ice sheet? But water flow going uphill nonetheless. We were pretty jazzed about that. We thought, wow, that's cool. That's cool. But there was one other mystery in this survey that we had. So here are the mountains, and you can see the ice. We weren't able to date the ice because there's not a good, there is not a good ice core there yet. But you can see there's water in the valleys, and there's mountains all over, and there's water on this side. But what was weird was there was a place that the layering didn't seem to stay flat, or roughly flat. There was something that looked really weird. It looked like that. Now, okay, so this is right in the middle is about 2,000 meters of ice. So this thing is about half of the ice sheet thickness. And being good, skeptical scientists, here are the mountains, and here's one of our water bodies. Being good scientists, we were totally skeptical. We thought, okay, we have really screwed up. This is the biggest error in our data yet. We are getting sideswipes. Something is happening. This can't be real. But we saw this in line after line after line. And when we looked at it, it turns out that each one of those upward flowing river valleys was connected with one of these bodies. What we had found was not only water flowing uphill, but when it reached the cirques in the valleys where the ice got thin and the gradient in the ice sheet got steep, that the water froze back on. So we are actually seeing sort of from melting at one end of the valley, water being driven uphill and freezing back onto the base of the ice sheet. I realized I forgot to tell you why it was melting at one end. The ice sheet can only hold so much, can only support so much ice before, even though it's minus 50 at the top, the geothermal flux at the bottom is going to bring the base of the ice sheet to the melting temperature, which is about minus 2. It's not a pressure issue. It's actually the geothermal flux at the base. So here what we were doing was, even though there's melt where the ice is thick, when the water reached the thin area, the water was refreezing back on. So the East Antarctica is kind of like a place you could not imagine if you just were looking at the top. You couldn't imagine that as you sat at the end of that runway, listening to the snow, that underneath of you were lakes, mountains that hadn't been exposed for 30, not only had no human ever walked on them, they hadn't been exposed for 34 million years, but we also had rivers, lakes, and water running uphill. It was one of those, and it was only possible because the international science community worked together. I think we should just do a little bit of West Antarctica because that's what's in many people's mind. This is mostly below sea level. Here's sea levels here in the blue on the right. And you can see it's not as thick. Remember, East Antarctica is up to 4 kilometers thick. It's about 2.5 kilometers in West Antarctica. And it is more susceptible. It is the one that is younger because it took longer to grow. It's harder to grow an ice sheet in an ocean than it is on a mountain. And it is easier to have it collapse. When we look at it, it also doesn't have as much excitement. It's kind of, here's the topography. I mean, that's not anywhere near as exciting. It's also younger. When you look at the layers, it's only the oldest layer you see is only 68,000 years. Remembering, we were seeing ice that's 800,000 years old in East Antarctica. But it sits in a very different place. Not only is it sitting on mud below sea level, it's a much more active terrain. It's that we discovered, as Dean commented, we discovered an active volcano underneath the ice sheet here. And what does an active volcano underneath an ice sheet look like? It basically, you see a round caldera. On the surface, you see it sagging down because of the heat coming in. You're actually making a hole in the surface. That was the indication that it wasn't just a little peak, that actually the ice sheet was showing us there was heat coming in and being melted at the bottom. We didn't have as good layers in our radar back then, so I don't have a beautiful image to show it sagging down in the over the volcano. So I feel like we absolutely, you could ask me to talk about almost anything, and I will touch on ice sheet change. I think people have asked me to talk about sunken ships in the Hudson River, and I've managed to slip in sea level rise into it, because I feel like we should all be aware of the evidence of our planet changing so that we can be spokespeople to our communities. So remembering that West Antarctica sits in a shallow ocean, what are the signs of change? One of the first signs of change, we'll just look in the upper left, is sort of the very emblematic loss of the ice shelves on the peninsula, that they disappeared progressively south as the surface temperatures warmed. So that was kind of the first indication that the ice sheets were warming and shrinking. Though more recently, we've been able to demonstrate that the ice sheets are speeding up, losing elevation and losing mass. So this is, we're going to zoom in and look at some movies of this. But the change is really focused in this West Antarctic region, where the ice sheets are most susceptible to changing ocean temperatures. So this is one of my favorite animations. We're going to look at how the ice sheet in the 1990s was moving about 2 kilometers a year. This is one of those giant glaciers. They call them glaciers or ice streams. And by the 2000s, it had sped up to 4 kilometers a year. That's a doubling of moving of ice into the ocean. At the same time, and I like to think of this as, you can see the elevation change. And we can look at this again just because I think it's so much more powerful if you see the evidence as opposed to me telling you. Where it's yellow, you're seeing the surface elevation over that same period that the ice sheet sped up, the ice sheet dropped. And it dropped 60 meters. It dropped because it's being stretched. Ice is kind of like cheese. If you stretch it, it gets thinner. So let's just look at that again just because it's it's worth everybody really understanding that and as a scientist, we really look for those independent measurements. And the velocity is made by looking at, in essence, surface feature tracking of the ice. So you can see that that's one measurement made with one set of satellites. And then the elevation change is made with a separate satellite. It's been done with both radar and laser from space or from aircraft. But what you can see is the elevation dropping as the ice sheet speeds up. And so those are two measurements. Very powerful third one is we can measure gravity from space. And gravity from space, this is called the GRACE mission. It lets it's one where you can actually see the mass loss in the same place. Very sensitive pair of satellites chasing each other in space, actually watching each other move up and down, measuring the gravity. And what you can see is, while there's some blue in the upper right. It was a very snowy set of years here, and there actually was mass gain in this part of East Antarctica. The very strong, clear, dominant signal is the loss of mass. In the same place we saw the ice sheet speeding up and losing elevation. So very clear signature that West Antarctica is losing mass. I could show you the same things for Greenland, just in case anybody's neighbor ever asks them. The same signals are there in Greenland, but we're talking about Antarctica today. So this is really, what I consider the ice sheet is really unforgiving, because we're starting to, these are places around the globe that we see where human beings have put in tide gauges. Tide gauges aren't really very fancy tools. They're kind of sensors that measure the water going up and down and up and down and up and down. But they're pretty cool because they've been doing it for a long time. And first look at the left, and just picking your part of the world, pretty much all the arrows are going up there. That means all those places sea level is going up. Right? And it's going up on the order, most of them are on the order of 2.7 millimeters a year. I like to think of the one on the upper right, just because, that's right near that end of the Verrazano Narrows Bridge. It's right there, in lower Manhattan. If you ever took the ferry to see anything in New York Harbor, it's right there, but it's been there since the 1860s. And you can see it's pretty relentless. What does 2.7 millimeters a year mean? What it means is if you put your hand on your leg, somewhere below your knee, that's how much sea level has gone up, probably since my grandmother was born, right, in the last 120 years. So we have already started to see sea level going up. And it's about the same here in the Wellington curve is the one below. It's only been there since the 1950s, but it's about 2.7 millimeters a year. Pretty much the same. This isn't Antarctica yet. This isn't Greenland yet. This is mostly the oceans warming. We're not really starting to see the input from the ice sheets yet. Yeah, right. So what is that? So this is really why, when you look at it, you realize that the ice sheets have been there a long time, that they have a history of collapsing, that we see change now. We see that the oceans are warming. And it's really time to look forward. And this is one of the real challenges. It's what a number of us spent today arguing and talking and discussing, how it is. Now what this is mostly looking forward. This is a timeline that starts in 1950 and goes up to 2010. And the top one is CO2, depending on what we as humans get our act together and do. And the bottom one is different future sea level rises by 2100. And you can see, the high end is about 1.7 meters and the low end is 40 centimeters. And this is what we're all working to try and improve, because I can tell you the policymakers we were talking to today were saying, so when are you going to be able to tell us exactly one of those it is? And what we really, all of us who are working in this space, are trying to get our understanding of the processes. How do those ice sheets work, right? Because if we don't have the processes right, we aren't telling the modelers the right things to do, so the modelers don't come out with the right answers. And then we also need to understand that history piece. We need to understand, have those ice sheets collapsed in the past? And what were the conditions? Was it 1.5 degrees above now? Was it 2? Which parts collapsed? Did the part I show you that was speeding up collapse? Or was it the part that's over near Scott Base in the Ross Sea? So this is really what we as scientists are working on pretty much at full time, motivating us. But we're also really struggling on how to communicate with this with communities, whether it's my community. I live on the Hudson River. We had Hurricane Sandy, or whatever it was called, Superstorm Sandy, and we had sea level, we had water places people had never imagined it would be. And we had more damage because of that sea level rise that had happened. Just imagine if people had never really gotten this around their head and they woke up one morning and there were boats up and down their main street and that had to be moved with a bulldozer. That's what it was, during Hurricane Sandy. So some of what we're trying to work with is how we communicate the change to communicate, how we communicate this uncertainty so that communities can plan appropriately, knowing that we're doing our best to understand, but we're still wondering what that range is going to be. So, in conclusion, I'd really like to leave you with this sense that Antarctica is ancient, beautiful, but unforgiving, and our footprints on this planet are large. And I think it's our responsibilities to build, a thriving, equitable, sustainable future for everybody. And that means that we have to figure out how every one of us can turn the knobs that we have. Every one of us has different knobs. Every one of us lives in different communities and connects differently with whether it's your local community or the group you work with, or maybe it's the people you do sports with. All of us have to figure out what are those knobs we can turn to make it so we reduce our carbon, we get to the place where we are not going to get those high end, and that we don't see these ice sheets collapse. And it's really a moment for all of us to communicate and think about what we can do as individuals, as citizens, as whatever you do professionally, whether it's scientist, engineer, lawyer, doctor, and what we can do in the global sphere. So with that, thank you for your attention, and it's been my honor to speak with you today.
I'm Rob Mackay, Director of the Antarctic Research Centre. So thank you, Robin. That was a really stimulating and engaging talk, particularly the journey. That's what I really, really enjoyed about it. As Earth scientists, I always hear this justification for us going to explore in Antarctica, that we know more about the moon than we do about the bottom of the oceans or that. And I kind of get a little bit irritated with that, because we do know a lot about our planet, but I think in Antarctica, certainly 20 years ago, that was a very, very valid statement. And it's really thanks to the research efforts and bringing together these huge teams that you have built from the ground up, this exploration, that we do actually start to know more about that really critical part of the ice sheet that governs how quickly it flows and how quickly it flows into the ocean. And I can speak from my experience as an undergraduate student. We thought of Antarctica as a big frozen piece of ice sitting on the bed, not doing much. It was Greenland that we had to worry about. And it was the discovery of these lakes. Vostok was known for a while, but we really didn't know about the other ones. We didn't know that they were connected by these rivers. And to be honest, this week I didn't know those rivers went uphill. But we do see these lakes are connected. There's a hydrological network that actually connects these lakes. And it's fundamentally changed our view of how Antarctica works, and it's gone from this static piece of ice to something that we actually are worrying about and potentially could be a bigger player to sea level rise than Greenland. So really it is a journey of discovery. Sometimes it's those discoveries you don't want to find. So yeah, it wasn't great news on that, but there is that message of hope in there that we can change our behaviour and potentially save those ice sheets. So the discovery of these water networks, what Professor Bell didn't really touch on are her contributions to actually understanding that topography. You've been fundamental actually understanding how does the bedrock under Antarctica affect how those warm waters melt the ice sheet. That really astute question up the top there about protecting that ice sheet from those warm waters. The geology, mapping that is fundamental. So yeah, fantastic talk, a real journey, but did see that message of hope, and particularly walking the walk and sailing that sailing boat. You know, really important that actually there's a message to how to behave sustainably. So just on behalf of Te Henare Waka and the Antarctica Research Centre, just thank you again for your talk. It was fantastic.